In today's lesson, we're going to look at the determinant of a matrix. We're going to know how to calculate that, and we're also going to know what its geometrical significance is. So we're going to start with the transformation represented by the matrix 3, minus 2, minus 1, 3. We're going to look at its effect on the unit square, which is the square with vertices at 0, 0, 1, 0, 1, 1, and 0, 1. We're going to find out where each of those vertices are mapped onto, and then we're going to look at the new shape created by this image and see how the area in particular of this square is affected. So at the minute the area is 1, we're going to work out what the area is of the new shape. So if you can just pause this slide for a second, I'd like you to work out the image of each of the 4 points, A, B, C and D, plot them onto the grid and then look at the new shape that's created. Okay, so first of all, point A, 0, 0, is mapped onto 0, 0 by the transformation. Point B, 1, 0, is mapped onto 3 minus 1. Point C, 1, 1, is mapped onto 1, 2. And point D, 0, 1, is mapped onto minus 2, 3. So we can join those up and we can see that we get a quadrilateral, but the area is different from the quadrilateral originally, the square originally. So we can actually say that the new area is 7 times larger than the old area. So the area of that new shape is 7. We're going to look at how could we have told that by looking at the matrix of the transformation. So if M is any 2 by 2 matrix representing a transformation of the 2D plane, we can calculate a number called the determinant of that matrix, and that number tells us the area scale factor. So it tells us if any shape is transformed by that transformation, how much larger or smaller will that shape become. So the notation for determinant, we can either write det in brackets M, or we can use the 2 lines that we've previously seen for modulus. We can put 2 lines around the letter M, and that means the determinant in the context of matrices. The way you calculate the determinant of a matrix, if the matrix is A, B, C, D, we do A times D minus B times C. And the number that we get as the answer, that is the determinant of that matrix. So for each of these 2 matrices, A and B, I'd like to find the determinant of each one. Then I'd like to multiply the product AB and BA. Now they won't always be the same answer because matrix multiplication is not commutative. Once you've found AB and BA, then find the determinant of AB and the determinant of BA. I'd like to write down what you've noticed about the relationship between those. So pause the slide now and calculate those things. Okay, so the determinant of A will be 3 times 5 minus 1 times 2. So that is 15 minus 2, which is 13. And the determinant of B is 4 times 8 minus 6 times minus 2. So that is 32 plus 12, which is 44. So using matrix multiplication, the matrix AB is given by 10, 26, negative 2, 52. So the determinant of AB is 10 times 52 minus 26 times minus 2, which is 572. And then using matrix multiplication to calculate BA, we get the matrix 24, 34, 10, 38. So the determinant of BA is going to be 24 times 38 minus 10 times 34, and we get the answer 572 again. So you will have noticed that the determinant of BA and the determinant of AB is the same value, even though AB and BA were not the same matrix themselves. You may also have spotted a link between the determinant of A and the determinant of B and these 2 determinants. If we calculate the determinant of A, times the determinant of B. In this case, we get 13 times 44, which is also 572. So that leads us to the rule that for any two matrices, the determinant of the product of those two matrices, AB or BA, is the same as the two determinants multiplied together separately, determinant of A times determinant of B. If you could now pause this recording and write down the matrices representing each of the three transformations below, and then work out the determinant for each one, and then write down what you notice. So the first one, rotation 90 degrees clockwise, about 0, 0. The matrix representing that is 0, 1, minus 1, 0. If we calculate the determinant, we get 0 times 0 minus 1 times minus 1, which is 1. For transformation B, we've got a rotation 30 degrees anti-clockwise, about 0, 0. That's represented by the matrix there. If we calculate the determinant of this one, we get root 3 over 2 times root 3 over 2 minus a half times minus a half. So that gives us root 3 over 2 times root 3 over 2 is 3 over 4. And minus a half times minus a half is plus a quarter. So again, we get 1. And then for the third matrix, rotation 225 degrees anti-clockwise, about 0, 0. The transformation is given there. Again, if we calculate the determinant, we get minus root 2 over 2 times minus root 2 over 2 minus root 2 over 2 times root 2 over 2. So that becomes, so root 2 over 2 times root 2 over 2 is 2 over 4. So we get positive 2 over 4. We then get plus another 2 over 4, which is 1. So all three matrices in that case are 1. And that brings us to the rule that the determinant of any rotation is 1. That is because when you rotate any shape, the area is unchanged. Now we're going to repeat that process for the transformations below. They all represent reflections. So again, pause the recording, write down the matrices that represent each of the three reflections and calculate the determinants to see what you notice. So the first transformation, reflection in the line y equals 0, is given by the matrix 1, 0, 0, minus 1. If we calculate the determinant of that matrix, we get 1 times minus 1 minus 0 times 0, which is just negative 1. For the second transformation, a reflection in the line y equals minus x, the transformation we get is 0, minus 1, minus 1, 0. Again, calculating that determinant, we get 0 times 0 and then minus negative 1 times negative 1. So that gives us negative 1 again. And then the final one, the reflection in the line y equals 2x is given by the transformation minus 0.6, 0.8, 0.8, 0.6. So that gives us a determinant of minus 0.6 times 0.6 minus 0.8 times 0.8, which is negative 0.36 take away 0.64, which again gives us negative 1. So what we notice is that all three of those determinants are negative 1, which brings us to the rule that the determinant of any reflection is negative 1. That is because the area itself is unchanged when you reflect a shape, but you can think of the shape as having kind of turned inside on itself, which gives the effect of it actually having a negative area. Finally, I'd like you to pause the recording again, write down the three matrices representing these three transformations, work out the determinants, see how they relate to the original transformation. So stretch in the x direction, factor 3 will be represented by 3, 0, 0, 1. The determinant for that is 3 times 1 minus 0 times 0, which is 3. For the second one, stretching the y direction, factor 2, it's given by matrix 1, 0, 0, 2. Its determinant is 1 times 2 minus 0 times 0, which is 2. And then for an enlargement, which is a stretch in both the x and the y direction, scale factor 5, we'll get 5, 0, 0, 5, giving us a determinant of 5 times 5 minus 0 times 0, so 25. So this rule is quite easy to see. We just need to take into account the factors there. The determinant for a one-way stretch, like in A or in B, is the same as the scale factor for that stretch. However, in C, we've got an enlargement, which is a two-way stretch. And in that case, the scale factor is squared to give us the determinant because the area is being enlarged in both directions. So for C, we've got 5 squared, which is 25 for the determinant. Now please complete exercise 7C on page 150.